Welcome to our video, How Climate Models Predict Our Future. During the next few minutes, we will delve deeply into the fascinating world of climate science. We'll learn how scientists use complex models to forecast future environmental conditions and what those predictions might mean for life on Earth. So, get ready to explore the high-tech tools that are shaping our understanding of the planet's future. Let's venture into the heart of this fascinating subject together. 1. The basics of climate models. Climate models are powerful tools that scientists use to understand and predict future climate conditions. Essentially, they are complex computer programs that simulate the interactions of the atmosphere, oceans, land surface, and ice. To put it simply, think of them like weather forecasts but on a much larger and longer scale. Climate models are built using mathematical equations that represent physical processes. These equations are based on fundamental laws of physics, and they help scientists understand how the various elements of the Earth's system work together. While these models are sophisticated, they are not infallible and come with their share of uncertainties. However, they provide critical insights that help us prepare for the future. 2. The role of historical data. Historical data plays a vital role in shaping climate models. Scientists rely heavily on past climate records and paleoclimate data to validate their models. This data includes temperature records, ice core samples, and sediment layers that provide clues about conditions on Earth thousands of years ago. By comparing model outputs with historical data, scientists can tweak their models to improve accuracy. It's like tuning a guitar. Each adjustment brings it closer to harmony. These validations ensure that the climate models are not only forward-looking but also grounded in reality. Historical data acts as a bridge between what we know and what we aim to discover. 3. Simulation of natural processes. Climate models simulate a wide range of natural processes. From ocean currents to atmospheric pressure systems, these models seek to replicate real-world conditions. There are various kinds of models, and some are more focused on specific elements like ocean models or atmospheric models. This level of complexity is crucial because the Earth's climate system is a web of intertwined processes. For instance, let's consider the effect of volcanic eruptions. Climate models can simulate how a major eruption might block sunlight, leading to temporary cooling. Such detailed simulations help policymakers and scientists prepare for various scenarios effectively. 4. Factors influencing climate models. A plethora of factors influences the efficacy of climate models. One of the significant elements is the sensitivity of these models to greenhouse gas emissions. Climate models often run different scenarios based on varying levels of carbon dioxide and other gases. Other influencing factors include solar radiation, aerosols, and even changes in land use, such as deforestation. Think of the Earth like a giant orchestra, with each factor representing an instrument. Any change in one can affect the overall harmony. These factors add to the complexity of the models but also make them more comprehensive and robust. 5. The importance of resolution. Resolution is a vital component of climate models that assists in predicting local climate conditions more accurately. Higher resolution models are akin to a high-definition picture compared to lower resolution ones. They provide clearer, more detailed images, allowing for better insights. However, higher resolution models demand more computational power and are more resource-intensive. Despite the challenges, the enhanced precision they offer is invaluable for understanding local climate impacts. High or low, the choice of resolution affects how specific or generalized the predictions are, influencing policy and localized climate action. 6. Predicting extreme weather events. One of the most critical outcomes of climate modeling is the prediction of extreme weather events. By analyzing data and simulating conditions, these models help forecast phenomena like hurricanes, droughts, and floods. These predictions are not just scientific exercises, they have real-world consequences, guiding emergency preparedness and infrastructural investments. For example, knowing in advance about potential flooding can lead to proactive measures, saving lives and properties. While they can't eliminate uncertainties, climate models significantly help in managing uncertainty and risk. Accurate predictions are a lifeline for countries vulnerable to extreme weather. 7. Challenges and limitations. Despite their advantages, climate models have their limitations. Predicting the Earth's climate is a Herculean task that comes with multiple challenges. Even the best models run into issues like computational limitations and uncertainties in data inputs. There's also the challenge of accounting for human behavior, which can drastically alter future emissions. Unpredictable variables, such as unforeseen technological advances or policy changes, further complicate forecasts. Nevertheless, scientists continuously work to improve models, learning from past errors and incorporating new data for more reliable predictions. These limitations, while serious, are not insurmountable hurdles. 8. Interpreting model outputs. Interpreting the outputs from climate models is no simple task. Once the data is generated, it needs careful analysis to convert into actionable insights. This requires collaboration between scientists, policymakers, and even the general public. Model outputs are often expressed in terms of probabilities rather than certainties, making interpretation an even more delicate task. The goal is to translate complex data into understandable formats that can guide decision-making. Consider it as decoding a foreign language. Every interpretation needs context, understanding, and an appreciation of nuance. The end of the summary.